Everyone, my name is Nahid Hossain. I'm going to be presenting dependency preserving data compaction for scalable forensic analysis. In the recent years, large companies have been the target of stealthy long-running attacks. These attacks spans in the durations of months to years. Once these attacks are detected, forensic analysis is initiated to find the entry point of this attack and the impact of these attacks on the system. So for performing forensic analysis, data worth from months to ranging to years needs to be stored in the system. The amount of data that it requires to be stored gets pretty large very quickly. For example, in an enterprise with 1,000 hosts, it can produce petabytes of data per year. The issue is not just with the storage cost. To perform forensic analysis on this huge amount of data can take the time it can take and dramatically slow down. So the need for data compaction is needed here. Our goal is to work with a readily available system called data, such as Windows ETW and Linux audit logs. Even though fine-grained dependency tracking can improve the forensic analysis, such tracking is not feasible cannot be feasible in large-scale deployment. Most of this fine-grained dependency tracking requires instrumentations. That is why, as there could be hundreds of binary applications running in the system, it becomes unfeasible to deploy them. Our second goal is able to reduce the data volume that does not change the forensic analysis result. So events can be dropped that will not change the result of the forensic analysis. Our main contribution is the two novel graph-based reduction techniques called full dependence and source dependence preservation. Using these two reduction techniques, we are able to reduce 5 to 19 times of the total number of events in the logs. We have developed efficient algorithms and optimization techniques for implementing these reductions. Algorithms and optimization techniques allows us to analyze the graph by 1 million events per second per core. We have implemented compact data representation techniques, which allows us to store the data in offline mode, which is 35 times smaller than the actual audit data. Also, in our graph, each one of the events takes less than 5 bytes to be stored in memory in the original data. Most of the forensic analysis considers the content of the log as a dependence graph. In this graph, the nodes are subjects or objects. Subjects being the process, and objects being file and network connection, etc. The edges between these two nodes are considered as the dependents, which are timestamped events oriented in the direction of the information flow. For example, at time 3, information is flowing from the node P to node C, so C has a dependence on node P at time 3. To perform in forensic analysis, to find the entry point of an attack, we mark one of the nodes as suspicious and we backtrack it to find the entry point of that attack. For example, here, if we mark the node C as suspicious, we can backtrack it to the network address a.com. Once we have found the entry point of an attack, we can perform forward analysis from it and see which are the nodes in the system that got potentially compromised. For example, in this example, b.com, if we consider b.com as the entry point of an attack and perform forward analysis from it, P, E, Q, and L could be potentially compromised. But C is not compromised here, because even though C has a dependence on the node P, the dependence arrived before the node P got compromised. So here are some of the reduction techniques. The reduction techniques can be categorized into two categories, log-based and graph-based. Log-based techniques examine a sequence of events, and depending on the local information, it decides if it can be eliminated without affecting the dependencies. Graph-based techniques construct a dependence graph, which uses the graph reachability property to prune out any sort of redundant events. It can leverage the global context for more powerful reductions. So let's look at a very simple log-based reduction techniques where it merges the successive events if they are identical. For example, here the first two events in the log and the second two events are identical. So these events can be merged into one. But the problem arises if there are intervening events in between those those identical events. For here, A reading from F1 is intervened by the event B writing to F2. Even though they are completely independent events, the run merging technique cannot perform any sort of reductions on them. Xu et al. Improved on this idea by allowing the continuing merging these identical events if the intervening events are performed on a different node or different objects or subjects. So here, even though A reading from F1 and B writing to F2 are completely different events performed on different objects and subjects, so this can be merged together. So the reduction is now performed. But the limitations of their technique is they take the context, they don't take the global context into considerations, they look at the local context. So which does not, which it becomes very difficult to perform merge on very common scenarios such as pipes. In this example, the process P and Q are communicating each other through a pipe E, but as there are some intervening events in between them, and their technique cannot perform any merging. As you can see, an outgoing event from the node E at time 3 is happening in between the incoming edge at time 2 and 4. So here's where we give our approach on full dependence preservation. We look at, so we allow to continue merging the events if the intervening events don't alter the global dependency of the nodes. For example, over here, the global dependence of the node P does not change between the time 2 to 6. So these events can be merged into one. Also, for the node E at time 3 to 7, only global dependence it has is on the node P. Other than that, it does not have any other global dependence. So these three events can also be merged. As a result, we can perform the reduction, and this is the reduced graph we can get. We also propose another technique of source dependence preservation, which takes a step further from full dependence and uses the intuition for forensic analysis to perform further reductions on it. As I've mentioned before, forensic analysis, during forensic analysis, we perform backward analysis to get to the entry point or the source node, and from the source node, we perform forward analysis. So in this preservation technique, we only preserve the dependency from the source nodes, and the source node being there's no incoming edges. For example, in this example, f dash has a source dependence on the node f, which is introduced at time 4. But the events at time 5 and 6 does not introduce any new source dependence for the node f dash. It has already introduced, it can only introduce the dependence on node f. So these two events can be dropped. Source dependence preservation is a more powerful technique than full dependence preservation, which can drop all the edges that don't introduce a new dependency on source nodes. Even so, as you have seen that taking into consideration global context, we can perform further reduction. But even though it is powerful, it is very expensive to compute on a time-stamped graph, because calculating the reachability on the graph calculating the reachability on the graph increases linearly with the size of the data. So also we cannot, like in the standard graph, we cannot cache and reuse. We cannot cache the dependency because the dependency on the timestamp graph changes over time. So we cannot cache them and reuse them. So our solution to it is converting it to a standard graph by versioning the nodes. Although because versioning increases the storage space, we have developed optimization techniques that reduce the number of versions by 20 times. On an average, just one in our system, only 1.26 versions are created per nodes. Here is a timestamp graph that has been converted to a version graph. A version is created whenever there's an incoming edge to a node. For example, S has a single incoming edge, so we create one version of it. G has two incoming edges, so we create two versions for the node G, and so on. So now we propose some of the optimization techniques. Our first optimization technique is redundant edge optimization. So in this technique, we say that if there's already an incoming edge from the latest node to the current node, then any future nodes can be discarded. Here, there's already an edge from S2 to G3, so we can discard the edge S2 to G5, and hence reduce the number of versions. So similarly, we can do that for T, the node T. Another optimization technique is the redundant node optimization, where if a node has not been observed or does not have any outgoing edges, we can merge. We say that for any incoming edges, we do not create any new versions for it. For example, here, S0 does not have any outgoing edges, so there is no change being made. So there's no it wasn't observed. So this S0 and S2 can be merged into one node. Same goes for G0 and T0. In ours, we have also performed some cycle collapsing optimizations, where if two nodes are in a cycle, we discard the events between these two nodes and consider them as a supernode. So here is the optimized. So here is one of the graph. There's a timestamp graph which has been converted into the optimized version graph in our system. Now I'm going to talk about the experimental evaluation. So in our evaluation data set, our system performed in the DARPA Transparent Computing second adversarial engagement. We collected data. We had data from Windows and Linux desktop, which may have spanned on the times of 7 days. This data contained benign activities such as reading from the web browser, email clients, reading and writing to files, etc. It also contained attacks involving the full APT lifecycle, such as drop and execute, file exfiltration, privilege escalation, etc. We also collected data from our lab spanning from 7 days, from a file server, a web server, and a mail server. This data also spanned on 7 days. So here are the number of events that contained in each one of the data. For example, the Linux desktop, there were 73 million events. Our web servers, there were 14.4 million events. So using our reduction techniques, here's the amount of reduction we achieve on those data sets. The first 3 data sets are the data set that we collected in our lab. The last 2 ones are the one from the adversarial engagement, second engagement. We also implemented Xu et al.'s algorithm to compare our work with them. As we can see, our full dependence and source dependence perform much better than their technique, as it takes the global context into consideration. Here the average number of nodes, average number of versions we create in using each one of our reduction technique, optimization techniques. With no optimization in our system, each one of the nodes would generate 25.58 node versions per node. With adding redundant edge optimization, it goes down to 9.14 versions per nodes. And adding redundant node optimization, it further goes down to 3.01 versions per node. And adding cycle collapsing optimization, we go down to 1.26 versions per node. Using our compact data representative techniques, we are able to store the data for offline investigations, for offline investigations. So we can store the data in a compact way, which is 35 times smaller than the original audit log, which is 24 gigabytes. And using source dependence, we can further reduce it and store it, which is 41 times smaller than the original log size. The dependence, so this is the main memory size it takes for each one of our graphs, for the whole graphs. We had, for all the 5 data set, we had 100 million events, which can be stored in a compact way in memory only 26 megabytes using full dependence, and using source dependence, it takes 248 megabytes. Our system also participated in the DARPA third engagement program. Here are some preliminary results because the engagement happened after the submission of the papers. We were not able to investigate it further so that this information is not in the paper. The data set on the third engagement was 10 times larger than the ones in the second engagement. The Linux desktop had around 800 million events, which we were able to reduce 70 times using full dependence. Our Windows desktop contained 70 million events, which was reduced by 10 times using our full dependence. So the summary from this, we can say that the larger the data size gets, we are able to achieve further reductions on it. The main reason is having long-running processes, because long-running processes becomes the global dependence becomes stable as time moves on. So as a reason, full dependence was able to eliminate most of the operations. So here's the impact of reductions on our forensic analysis. In our paper, in theory, we were able to say, we have proved that full dependency preserves the forward and backward analysis results for all nodes. Source dependency also preserves the backward analysis result for source nodes. But in practice, we also have seen the similar behavior during the DARPA adversarial exercise. During the engagement, we did not have any prior knowledge about the attacks. We performed forensic analysis in real time while the full dependency reduction was going on. Our analysis started when an attack is detected by our system sleuth, and we perform forward and backward analysis from that point on. Here is an attack graph that has been generated in our system automatically. This is generated completely automatically, where an object called Nexus was dropped and executed. We performed some information gathering and exfiltration, and also there are some privilege escalations to it. This graph was completely generated automatically in our system. So here's the number of entities. As we can see from here, the number of entities using any one of the reduction techniques does not change. Even with the base techniques, the number of entities, and with any sort of reductions, we see the number of entities has not changed in this case for all of the attacks that we've seen. Okay, here are some of the related works related to the log reductions. LogGC, ProTracer, MPI, all of them uses fine-grained dependency tracking. We mainly target the coarse-grained auditing system, which can be actually deployed in large enterprises. Shu et al.'s systems performs log reduction based on the local context, which is why is unable to achieve higher reduction than ours. There are other papers related to reductions, such as provenance collection techniques, PAS, performs, run merging technique, and many more that is discussed in our paper. So in summary, we have developed some highly effective reduction techniques for the audit logs, where we achieve 5 to 19 times reductions on the number of events. We have developed efficient algorithm and optimizations for full dependency and source dependence technique. We presented compact data representation techniques to achieve over a magnitude of reduction in storage and memory size. Thank you. I'll take any questions.
Hi, Adam Bates, University of Illinois. Really interesting work. I had a question about the source dependence algorithm. Are you applying that on individual nodes or with respect to like a network of nodes?
You mean for each node, what is the dependency that you are storing?
So with the source dependence, the idea is that we preserve reachability to the source nodes that don't have any incoming edges.
Right.
So are you doing that on each node in isolation? Or sorry, I'm using conflation here. Each computer in isolation, are you applying that, or are you doing this across a distributed system?
So currently, our system is for per host basis, or this is implemented in the per host.
So I'd be really curious to see, it seems like there might be some troubles applying this in the distributed context because those source nodes you're preserving reachability to are sockets that represent a connection to another machine.
Right.
And so it seems like there's a risk that we're conflating multiple events that actually represent autonomous units of work that are happening on that other machine. And so like looking back to the RTAG paper, there might be issues with tracing multiple workflows that are happening between two different hosts.
So we are working on implementing the distributed system where inside the intranet there will be multiple hosts running on multiple of these machines, and we would know actually how to connect between them.
Okay, cool. Yeah, maybe we can talk about it offline.
This is actually what we are currently working on.
Right on. Oh, thanks.
Any other questions?
Hi, John Criswell, University of Rochester. Not so much a question, but a comment. While watching your presentation, your algorithms look a lot like the algorithms that we use for analyzing and optimizing programs in the compiler world. Right? So your versioning looks a lot like SSA construction. Your cycle reduction, where you're creating strongly connected components, is a lot like call graph analysis in the DSA algorithm, or like cycle analysis in Anderson's points to analysis algorithm. Have you been inspired by program analysis algorithms? And if not, do you think it'd be worth looking into that literature to see if there might be something that might inspire further optimizations of these graphs?
Thank you for the comment. Yes, I'll definitely I haven't looked at it personally into those algorithms. I've seen some of them, and our main intuition was to use some of those versioning techniques, which in general just says that it should inflate the size of our system in forensic analysis, but we showed that using those versioning techniques, we are trying to reduce the data size. And definitely I'll look at some of more further optimization techniques in the compiler and see if we can further use it in our system.
Yeah, it'd be interesting to see if there's actually kind of a correspondence between these two worlds, right? Because they're both looking at data flows, they're both looking at dependencies and whatnot. So it may not be quite the same, but it looks pretty similar.
Right.
Okay. Thank you.
Anyone else? All right, let's thank the speaker one more time.